Go to the specification, select tension. But before, okay, now before I go ahead with the analysis, I will use some option instead, which is known as the auto load combination, to create the load combination, because load combination is a very important feature. This is just like an envelope of different loading combination, which is basically the manifestation of some critical condition for designing. Now, see here, if we go by the conventional way of defining the load combination, then it's a very straightforward. Go to this loading, then define the load combination and all. But there is also a very smart way to define the load combination, and it will also reduce all those manual intervention. It's a very cumbersome process to manually calculate those factors and select the combination. And if there are, say for example, more than 10 different primary load cases, then there would be more than 10 different combination cases. So every time you create them manually, it's very painful, and also you might have the risk of inputting some wrong or some unknowing factors or the combination sign. So what we suggest is go by combining with the auto load combination. First of all, it's a very faster way. You just straight away select the code that you're using for combining, and then it will also reduce the risk of committing any mistakes. So here, for example, I'm selecting one of the codes like IS456 and IS800. You can also change this combination rules. There is an option to edit the combination rules, and also you can create your own combination rules. Now, once you are in the automatic load combination from this dialog box, you could see something called edit auto load combination. And there you could see some rules to create new set of combination rules. So you can create your own set of combination rules, and these rules would be saved by some name. And next time, if you click on create a combination and select this drop down list, you can see your recently created combination rules. So anyway, this is a very smart feature, and not only that, instead you have the option for combining the loading, primary loading by the load combination, but also you have the option called repeat load. Now this is very important. Like let's before I go further, let's explain what exactly is a repeat load. Uh, Repeat load is a similar combination feature, just like some conventional load combination. The conventional load combination is not going to perform the analysis for that specific combination cases. It will only perform the analysis for the primary cases. For example, a combination case is like 1.5 dead load plus live load or the win load. Then program is not going to solve for all the combined effect. It will solve for all the primary load cases, and then it will algebraically sum up the response of those primary loading actions and then multiply them with some factor and considering whatever the sign you have used, and it will deliver you the final response. That means a program is just using the post-processing values of the primary load cases. It is not going to solve for the combined effect. Now, when it is okay to use the load combination, that's very important. The load combination is only allowed if your structure is behaving linearly. Now, what is the linear combination? Linear combination is something like superposition. Uh, Most of the cases for the linear elastic analysis is behaving as a linear analysis. That means as it's linear, so you can linearly superimpose the primary effect. In that case, you can use the load combination. But if your structure is behaving non-linearly, for example, you have invoked some P delta effect, you have invoked like direct analysis, you have invoked like tension only or compression only members or compression only supports. These are basically not linear, they are behaving non-linearly. So you can find more details on this linear response and the nonlinear response through different community posts, and I also have some posting in the Bentley community site where you can find detailed discussion on this topic. So to summarize it, if the case is the structure is behaving nonlinearly, then you need to use the repeat load. Now, in your case, or in our case, in this model, we have used the bracings as a tension only. So as I mentioned, the moment you are using the tension only or compression only specification, that very time you are considering the structure to behave as nonlinear. Now, as it's a nonlinear, we can't use the load combination. Now, there is a very simple interpretation of this with some sample model, just a small experiment. We have done it for the goalpost. Now, you can see there are two goalposts. In one case, we are applying the load from the left-hand side, and we are seeing the response in the bracings. These bracings are assigned as a tension only. Now you can see that when we are applying the load from one particular end, one of the bracing is experiencing the tension and another bracings is not experiencing any force because the tension only, and the moment it is experiencing compression, it is switched off. Okay, now go to the another scenario when the load has been reversed and it's been applied to the other point, other opposite point. Okay, now this time the other bracing is experiencing the tension. Fine. So till now we are okay. Now let's see when both the loads are acting simultaneously at the two location of that bracings that we have used in the primary load cases. So assuming that both the loadings are applied at the same point of time and they are equal and acting opposite. Okay, now if you do a combination or use the stat pro load combination, the conventional load combination, and perform the analysis, what it would do, it is algebraically extracting the response of the primary load cases. And in that case, it will show that both the members are experiencing the tension. But if you see it intuitively, just imagine what it could be the response in the physical sense. Just imagine when both the loads are applied in the opposite directions having the same magnitude, then of course none of them is supposed to experience the tension. Both will undergo compression. But if you are doing the load combination and perform the analysis instead, then it is giving a very misleading result, right? It is showing that both the members are experiencing tension. So that's the fallacy of using the load combination because we are using it for the nonlinear case. So in our case, we need to use the repeat load. Now let's see how it behaves if we define the combined effect by defining the repeat load. So we have defined the repeat load. Let's perform the analysis. Okay. Now after the analysis, now we can select the repeat load case. Now here you can see that none of the bracings are experiencing any form of tension because both are undergoing compression. Because in this case, program is indeed performing the analysis for the combined effect and just determining what is the actual response in the structure. So this is the key for this discussion is like in our structure, we have defined several set of bracings as tension only. So we are not allowed to use the conventional load combination. We are supposed to use the repeat load instead. So basically, it's the same way of defining. Just like a load combination, you will drag the basic primary load cases and define the factor, and it will assume the combined effect. Now, there we can do it manually for each and every load cases, but we can also do it with the auto load combination. The moment we select the primary load cases in the auto load combination, don't forget to select the create repeat load. It will automatically create the repeat load cases instead of the conventional load combination. Now you can see all the load cases are created. Now, if we click on add, you can see there are numerous load combination cases or the repeat load cases. So, isn't it a very helpful feature to curtail all those laborious practice of manually creating the combination cases? So, this is a very smart way of creating the combine effect, and then we can perform the analysis.
Now you can go to the post-processing mode where you can see the post-processing responses like forces, displacement, any kind of section forces. So all the different kinds of responses would be available in this post-processing mode. Now here you can see the axial force in this members. Now these are the bracings, cross bracings, which has been assigned with the tension only property. Now this is the illustration of the axial force. So you can also see the intermediate stresses develop inside the beam. If you select any of the section of the tapered member, then you can see the intermediate fiber stress so that you can understand that how the stress is being varied across its length. So just drag the slider like this. You can see that at every point or the four corner nodes, it is displaying the forces, that is the stresses. These are basically the actual fiber stresses. Now, uh, the moment you are dragging the sliders, the depth of the section is changing. It's kind of increasing and then decreasing. So you can see that is the stresses at every selected cross section along the length of that selected section would be displayed. So same way you can see the reaction. So this one looks quite good. I have seen the responses like displacement, moment. This all looks quite reasonable. There is no such abnormal spike in the displacement or the moment, and there is no such kind of abnormal drift in the structure. So the analysis looks fine. Also, we didn't see any kind of instability related warnings or any kind of error message. So we can go ahead with this model and we can further design the different components in that structure. Okay, now before I go ahead with designing, let me explain you that here we have selected two different kind of sections. One is built up and another is a cold form section. So basically these are the steel sections, but built up and cold form are different. Okay, now first we will start with built up sections. That means the normal sections. Then we will go to the cold form section design. Now, instead, before we go ahead with the elaborate designing, just want to let you know that in the uh, AISC and Indian code implementation, we can use the load envelope option to perform the uh, design check both for the strength as well as for the serviceability. Now, you might be wondering like what's the difference? Previously also we could use different parameters to perform the serviceability check. Serviceability means the deflection, and also we could do the strength check. But previously, in the previous scenario, that means without the envelope option, what you would have to do, you have to create two different set of parameters, parameter 1 and parameter 2. For example, in the parameter 1, you have defined the Indian code or AAC code, and within that parameter block, you would have to define different parameters related to the strength check, like UNT, UNB, then FILD, effective length factors, and so on. Basically, these are meant to perform the strength check. Now, if you want to do the serviceability limit state check, then you need to also create another set of parameter, say parameter 2. Within that parameter block, you would have to define the parameters related to the deflection, that is the serviceability. Now, what are the parameters related to the deflection? Like DFF, that is the deflection limit, then the reference nodes to count the, you know, the deformed shape to calculate the exact deflection. These reference nodes are denoted by the parameter called dj1 and dj2. So basically the idea is in the previous scenario you would have to define two set of parameters, parameter 1 and parameter 2, and after you perform the design you need to go to the output file and see, okay, for the member number 1, this is the ratio against the parameter 1, that is for the strength. Okay, and this is the ratio for parameter 2, which is for the serviceability. Now, first of all, it's very time consuming because you have to create two set of parameters individually for the same members, and also you need to refer to the output file and just compare which of those two ratios are guiding. Sometimes the serviceability ratio is more critical than the strength ratio. So, to curtail all those complex approach, we had come up with the envelope option. Within that load envelope option, you needn't have to create two different set of parameters. You need to create only one set of parameter, like parameter 1. Within that parameter, you just define the required parameters associated for the strength check and also for the serviceability check within the same parameter block. DJ1, DJ2, DFF and all. And just define that, okay, an envelope that you have created. I'll show you how to create that envelope and then fire the design. After analysis and design, program would report the ratio against the single parameter because you have defined within the same parameter block. Now within the same parameter block you can find the critical ratio, so you needn't have to refer to two different set of parameter and compare the ratios, and it will also show you, okay, this is the ratio against deflection and this is the ratio against strength. So let's see how we can use the the load envelope option and to perform the strength as well as the serviceability limit state check. Now here you can see I have already created the load envelope. Now I will show you how to create it. Now, for example, to create the load envelope, all you need to do, just below the load case, you can see a small title called load envelope. Just click on that and just click on add. Now you can see a small dialog box would pop up. It will have all the available load cases. That means the load cases that you have created, including the repeat load cases. Now, as you can see here, including the repeat load cases, we might have reached up to 30 or 40 set of different cases. Now, say for example, you have created all those load combos, including the combos related to the serviceability limit state. For example, for the strength, you might have used 1.5 times dead load plus live load, and for the serviceability, it could be like just dead load plus live load. So generally, you can create the load combination cases like that. Say, for example, first 30 cases for strength, um, and then the rest of the 10 or 15 load combo cases for the serviceability. So accordingly, you can uh, drag the cases related to the strength limit state and assign the type as strength. Just go to that type, just keep on selecting down. You can see the serviceability as well as strength. So first I will use the serviceability. I have selected these set of load combos associated with the serviceability, and then I have used the remaining set of load combos and assigned it with the type strength. The program can understand that, okay, from 1 to 30, these combos are meant for the strength check, and from 30 to the remaining load combos are meant for the serviceability limit state check. Now, my load envelope definition is over. Now, so to invoke this load envelope for designing is very straightforward. Just in just on top of the envelope, you need to insert the command called load list, then space, then env, which stands for the envelope, then 1 and 2. That means you have instructed stat that, okay, perform the design for both the set of envelopes, and envelope 1 and 2. Envelope 1 is for strength and envelope 2 is for serviceability. So had you uh, uh, instructed only envelope 1, then stat would only selected the load combos which are meant for the strength check, and accordingly it would have performed the design and for the envelope 1. Now here we have selected both the envelopes, so it will first do the strength check for all the load combos under the envelope 1, that is something around from 1 to 30, and then from 30 to onwards up to I think 35 or 40 in this case, it will treat as the load envelope for serviceability, and it will perform the deflection check for those load combos. So within the same parameter block, it will perform both the checks. Before we go ahead defining the different set of parameters, we have defined the envelopes. Now we will see how to define different set of design parameters. Here you might have seen that I've already created two different parameters, parameter 1 and parameter 2. These are not meant for the serviceability and strength definition that has been defined individually. These are the parameters representing the design for the normal built up section, and the parameter 2 meant for the cold form. I'll show you how to invoke those important parameters meant for these codes. Okay, now first select all the default parameters. So basically all the necessary parameters would be there. If you click on define parameter like this, you can see all the different set of parameters. Now parameters are nothing but the different set of criterias or the condition that you want to set before they perform the designing. For example, you want to set the FILD value with certain magnitude. Then if you want to control the effective length factor, unsupported length, and so on. So you can set all those controlling criteria from this parameter. Okay, now you can see there are a list of parameters. Now I'm not going to discuss all the set of parameters for ASC or Indian code. I'll just show you a few of the important parameters which is meant for the PEB. Basically, most of the parameters would be required, like FILD. If it is default. Like FILD is required if you do like built-up section or hot roll section. FILD would be there. So these are some common parameters, but I will show you some of the parameters which is specifically meant for the PEB because our discussion is based on the pre-engineered building. Now, pre-engineered building is basically, as I mentioned, the section that we chose are some custom section. These are not some standard hot roll sections. Now, basically, what happens? The designer first take a plate and then they see the drawing and accordingly they carve out the flanges and the webs, stiffeners and so on and cut them out of the plate and then according to the drawing and geometry they will assemble them, fabricate them, weld them together to give it to the final shape. Say for example the web tapered sections. Now web tapered section, if you might have seen some industrial structure having the tapered section. These are huge sections. Sometimes the depth is as great as 600 to 750 mm. Now, these are the sections which are whose web are generally gets tapered off, and these are not hot rolled because you are slicing out those shapes, tapered shapes, and welding the web and the flange by the method of welding. So these can't be treated as a pure hot roll sections because we are not bringing out the entire section with that cross-sectional shape directly out of the blast furnace and giving it the shape just in the molten state. So once it has been, it's not cold form, but it's like it's a built-up section. Okay, so the design rule, most of the design rule would be same, except few of the design rules which are exactly meant for the build-up section. So let's see what are the different design rules that separates out the built-up section from the typical hot roll sections. Okay, regarding all those design parameters, you can go to the help manual and also in the future point of time, I will try to come up with a separate training course specifically meant for discussing those parameters in detail. Okay, so I assume that you will assign most of the parameters like FILD, effective length, then unsupported length and all as per the design requirement. Okay, now here you can see I have purposely selected few of the parameters which is specifically meant for the build-up sections. These are like the code that I have selected is AISC. I will also cover the parameters equivalent to the Indian code. These parameters like TSP, TSD, STP. Okay, now see for example here, first of all, while we do the section classification, this is for AIC 360. When we do the section classification, which is a very important procedure for calculating the design strength of any member. The section classification is nothing but it is based on some geometrical shape of the section and also some manufacturing criteria like whether it's a build-up or whether it's a hot rolled. Now you can see that while we are trying to figure out whether the element is slender, compact, or semi-compact, So basically, we need to use the B by T ratio. Now, if you go to the AISC code table number B4.1.1a, you can see they have separated out this limit for the built-up section from the hot roll section. So basically, these guiding limits for the built-up section is not exactly same as the limit for pure hot roll ice shaped or any other sections, standard section, I mean. So here you can see this limiting width to thickness ratio is different. So program has to understand that okay, this is a built-up section. So while we categorize the element as slender or non-slender, we need to use these coefficient as a boundary for categorizing it as a slender or non-slender. So how program would know that whether the section that you have selected is indeed a hot roll section or it's a built-up section. So for that you need to use a parameter called STP. Here you can see. Now by default the STP value is taken as 1, which means um, the one is for the hot roll section, and second is the welded section whose STP value should be 2. So in our case, we are using the tapered web section. So basically, this is not a hot roll section. This has to be the built-up section. So we will select the STP value of 2 instead of 1. Okay, now first I will discuss for AISC, then I will come to the Indian code. Now, next is for the chapter G, which is mainly for the shear strength limit states check. Now, here you can see for determining the nominal shear strength, this equation is somehow related to the factor called H, which is the clear distance between the flanges, and coefficient or the ratio determined or required as H by TW. You can see this limiting value for the typical hot roll I-shaped section is not same as for the built-up or the welded section. So basically, when you are using the welded section, that means this H over TW ratio limiting point would be different. So how to instruct it? Same as you are doing it as a STP. The moment you are defining the STP, program would go to this code rules, and accordingly it will understand that okay, you have meant it for the build-up section, and accordingly it will search for the design rules meant for the build-up section. Okay, now the next is the stiffener, the web plate stiffener. Basically, stiffener is provided along the cross section of the or the depth of the web. The reason is most of these sections, the tapered web sections used in this kind of structure, these web sections are having a significant depth, just like a plate girder. Now, when it experiences immense stresses, then they might have the tendency to buckle out of plane. So, to resist them from buckling out of plane, we need to provide some stiffener vertically. So, for this stiffener, you need to provide the distance of the stiffener, and accordingly, program can calculate the different web plate shear buckling coefficient. So, what you need to do, you need to define the clear distance between those transverse stiffener. So how to define this? There is a parameter called stiff. If you provide the stiff parameter, then it will provide you the option to define the distance between that is the clear distance between the two consecutive transverse stiffener, and accordingly it will calculate all the different coefficients related to this clear distance, and it will further perform the design check. For AIC, basically, these two parameters are sufficient to differentiate the welded section from the hot roll section. Now, if you are using the Indian code, that is IS 800 2007, then also you need to provide some instruction to STAT to make it understand that okay, you have used the section which is basically a welded section rather than the typical hot roll section. Now, same as the ASC parameter in the IS 800 2007, we have the parameter called STP. The default one is uh, 1, default value is 1, which is for the hot roll section. Now, for this case, you need to use the STP parameter and set its value as 2, which is meant for the welded section. Now, the same thing, it will use the different condition meant for the hot rolled and the built up section using the section classification. Okay, so in the section classification, we have two different bounds, upper bounds and lower bounds for different classes like, as I mentioned, plastic, compact, semi-compact. In case of AS, it was slender or non-slender. So these boundary values vary for welded and roll section. And then we have the buckling class. Now, if you go to the clause number 7.1.2.2, then you can see there is something called buckling class of cross section, and there too they have ramified into two different category. One is for the rolled I-shaped section and one is for the welded I-shaped section. Now again there is some limit. These limits are not same. So once you have provided the STP2, then it will accordingly check the limit meant for the welded I-shaped section. Okay, now there's some other design checks. The rules for the welded section is not same as the typical hot roll sections, and one of them is the imperfection factor. You can see this alpha LT factor for hot roll steel section is different from the welded steel section. Similar to the ASC code, in the Indian code also, there is a check for the shear buckling. Here also you need to provide the information like the spacing of the stiffener. Here the command is TSP. So TSP means the spacing of the transverse stiffener. The default is 0. That means unless you provide any value, then of course this value is be taken as 0. So you provide the required value as you are going to provide the stiffener here. Next is the TST parameters. Now basically the TST parameter should precede the TSP because TST parameter is the parameter which would provide you the option to instruct whether you want to provide the stiffener or not. So basically the default is 0, that means you don't want to provide the stiffener. If you want to provide the stiffener, you need to set the value as 1, TST1, then only the TSP parameter would be applicable. Okay, so these are some basic parameters for the ASC as well as the Indian code that separates out for the parameters for the typical hot roll sections because it's a PB structure whose most of the sections are the welded section. So next is the parameters for the serviceability limit state. Now I won't assign for the entire structure, you can go ahead assigning for the entire structure. But just for typical explanation, I will choose one continuous physical member, and I will explain you how to assign the different parameters meant for the deflection check. The first is DJ1 and DJ2. DJ1 is basically the first reference node that we call it the DJ1, and DJ2 is the second reference node of this entire continuous physical member. Now, basically, DJ1 and DJ2 is nothing but it's like while the member is deformed, then it has to calculate some, you know, value of the deformation, right? How much it has deformed. Now, deformed means with respect to its own axis. Now, how will you calculate? You need to know that, okay, this is the member, and I will check the deformation of this member, right? Now, if you want to instruct that, okay, this is the member, how will you define? So basically, you need to provide some reference, DJ1 and DJ2, then the set of analytical members in between these two reference node would be treated as a member of concern. Now the deformed shape connecting from DJ1 and DJ2 would be accounted for. Next is the DFF, and this is a very important parameter, that is the deflection length over the maximum allowable local deflection. So basically this is the allowable deflection limit. Uh, you can provide your own set of value. Now this is very straightforward. Just provide the DJ1 and assign it to the required node, and similarly you can provide the DJ2 and then you assign the DFF. Now everything is all over. Now you have some other parameters. You can define some of the important parameters like ratio parameters, then LY, LZ, then KY, KZ, and these are the different parameters which is mostly used by the designer, but I'm not going to explain those parameters. So basically my purpose is to show you the important parameters meant for the PEB that could separate out from the conventional building parameters. And rest of the parameters are work same as the conventional hot roll section as well as the welded section. Okay, so I have selected this base for designing, and next I will go to the parameter 2 that I have already created. This is meant for the cold form section design. Now the cold form section design, the set of parameters are very much limited compared to the normal parameters meant for the hot roll sections. So all you need to do, provide the code, and some of the parameters, important parameters like spacing of stiffener, if there is any stiffener, but in this case there is no stiffener across the sectional depth of the selected cold form. If there is any stiffener, you provide it, or else you can use the default. And also if there is any specific um, uh, input for the ratio or the effective length, you can provide it. So I have provided track 2 to see the detail of the output. Now if you use the command called track to all, then all the members would be assigned, and I have specifically selected for the members of the concern. So for the analysis, it will first analyze the structure, then it will design. Okay, so it looks fine. So the first one I have selected, you can see the design outputs are detailed. This is, I think, for the cold form sections. Yes. Now you can see here in the same parameter, it has also performed the deflection check along with the strength check. So even if you now let's see for the cold form section, I think it was yes, this one you can see the cold form section has also been designed. Now, even if you double click on any of those purlins or the rafters which are assigned by the cold form section, you can see that in that dialog box there is a separate tab that will appear, that is the steel design. That means your steel design has been performed successfully. Yes, the section may be passed or failed, the status would be shown.